It's my honor to introduce Jianxiao. Jianxiao completed a CSST undergraduate summer program in my group in 2017 and was so excited about the work going on in quantitative biology from that experience that she decided to apply for and was accepted into our PhD program in biomathematics in 2018. Working in my group, Jianxiao has participated in a co-author in already 2 published papers, one looking at a clinical application of different treatments for bone density loss, and the other a more theoretical piece examining statistical computing aspects in large-scale observational data. Jianxiao is completing her PhD work in computational statistics, where she's focusing on using advancing compute technology to solve what once were computationally intractable problems in the healthcare domain. And with that, I'd like to invite Jianxiao to share her screen and kick off with her work. Perfect, your screen's up. Your video's still off, I suspect.
Hello, this is Jianxiao, and thanks for Mark's introduction. And today I'm gonna talk about how to address computational challenge in massive sample size survival analysis using GPU parallelization. And large-scale observational health study thrived in last decade with the development of digital health technology. But observational data such as claims and electronic health records is a rich source for conducting medical product research, especially comparative and effectiveness and safety study. However, it suffers from computational challenge. Because typical claims and EHRs contain millions of individuals with thousands of patient characteristics and up to 10 years of data per life. And statistical methods used in health analytics, especially in survival analysis, become computationally expensive as sample size grows large. First, let me briefly introduce survival analysis, where we're interested in time to event time. And the event we are interested in can be death, can be the failure of a treatment, and adverse drug event. We use survival analysis a lot in comparative effectiveness and safety study. For example, when we study the effect and safety of hypertension medication, we're interested in the time until a cardiovascular event, which is an effectiveness outcome to check if the drug successfully prevents a cardiovascular event. And we may also interested in time until abdominal pain, which is a safety outcome to check if the drug is safe to use. Sorry, I forgot to turn on my view. And the competing risk is another type of event that patients are also at risk. It either hinders the observation of the event of interest or modifies the chance of this event occurs. For example, when we're interested in hospitalization of heart failure, myocardial infarction might be a competing risk of this primary event because it may change the future risk of heart failure. And the standard Cox model, which is used a lot in survival analysis, just ignores the competing risk, while another type of model called fine-grained model takes competing risk into consideration. And now let's take a look at some math. So in Cox model, our data contains triplets delta I, yi, and xi. So delta I is an outcome indicator to indicate if the individual I experience this event or not. And yi is the shorter time of time to event time or right sensor time. And right sensor time is just the end of observation period. And xi is the p-dimensional vector of time-independent covariates in standard Cox model, but of course, we may extend it to time-dependent covariates later. And here I want to introduce the definition of risk set. Here is R of yi. So risk set at time yi contains all of the individuals that have not experienced event at time yi. In other words, they are still at risk at time yi, and that's why we call it risk set. And this is important for parameter estimation. And also for risk set, we can imagine that in the very beginning, when the yi is the smallest yi, all of the individuals are in the risk set because they haven't got event or they haven't died at the very beginning. But individuals start to live the risk set over time if they experience an event or we no longer observe them. And the parameter estimation follows the log partial likelihood, as shown here. So we can see that the log likelihood is actually the sum of each individual's likelihood contribution. And the problem here is we can see a risk set in our log partial likelihood equation. And so unlike in the usual linear regression or logistical regression, when individual i's likelihood contribution only relies on its own data xi, so here individual i's likelihood contribution also relies on other individuals in its risk set, R of yi. And this poses a computational burden in likelihood estimation. And fine-grained model is very similar to Cox model. The only difference is fine-grained model consider multiple types of events. So additional to the delta yi, and xi, we have an epsilon I to indicate the type of event. And by convention, epsilon I equals to 1 indicates the primary event, and equals to 2 indicates the competing event. And again, I want to emphasize the definition of risk set here. So here, risk set contains is actually the union of two disjoint sets. The first set is the same as in Cox model. It contains the individuals that have not experienced primary event or any type of event at time yi. But the second set contains the patients that have already experienced the competing event at time yi. We sort of still consider those patients in the risk set because they haven't experienced the primary event. So actually, fine-grained model study the time to primary event in the case that the patients are also at risk for competing events. So the log partial likelihood of fine-grained model is also very similar to Cox model. The only difference is we have a pre-computed weights on the second risk set here. And I also want to introduce the optimization algorithm that we used in parameter estimation. So we use CCD, cyclic coordinate descent, to cycle through the coordinates to update using a one-dimensional Newton steps. So the advantage of CCD is we actually reduce the high-dimensional optimization problem to a large set of one-dimensional Newton steps. So we don't need to deal with the inversion of a large Hessian matrix, but we only need to estimate the scalar gradient and scalar Hessians here. And since our goal of this project is to speed up the massive sample size survival analysis, so actually the first step we need to do is to profile our existing code and figure out which part is the most time-consuming part. And our profiling indicates that the computation of gradient and Hessians take more than 95% of the total model fitting time. So that would be our target for parallelization. And here I want to pause a little bit to summarize the previous background. of this project. So first thing is in Cox model and fine-grained model, likelihood contribution of a data point depends on other data points in its risk set in the survival analysis setting. And we use cyclic coordinate descent to reduce the optimization problem down to a large set of one-dimensional optimization problems. And the profiling reveals that the most time-consuming step is the computation of gradient and Hessians. And now let's look at some background of GPU computing that we use to speed up our massive sample size survival analysis. So let's start from the top to bottom. So we can see in a GPU, we have many threads, and many threads forms thread blocks, and many blocks are grouped together as grid. And here I really want to introduce is the memory hierarchy of this GPU structure, because this is very important for us to achieve optimal performance in GPU programming. So we have different kinds of memory hierarchy on GPU, and they have different properties. So we want to make use of them properly. So each thread has a local memory. This is a very fast memory, but it's only visible to this thread. Per thread local memory. And each thread block has a block shared memory. And this is very useful because all of the threads within this block can access to this shared memory and communicate to each other through this shared memory. And this is also on-chip memory and can be accessed very fast. And all of the threads across blocks, across grids can access global memory. So in terms of speed, the global memory access is the most slowest. So that's why we want to minimize it. And the shared memory and the local memory are all on-chip memory, and we can access them very fast. And here is an example of GPU kernel. This part defines the operation that we want to perform in this kernel. And in this example, it's just perform a matrix addition. Each time when we want to launch a kernel, when we want to invoke a kernel, we need to specify the number of blocks and threads per blocks that we want to execute this kernel. And here I also want to introduce two useful building blocks for parallel computing. So one is reduction and the other one is scan. Both of them are tree-based parallel algorithm. So in a reduction, our input is an array of elements, and the output is a single value. And this single value is usually the sum of this sum of all of the elements in this array when the reduction operation is addition. And in a scan, the output vector, the output is also a vector, an array. And for example, the first elements in the output array is actually the first elements in the input array. And the second elements in the output array is the sum of first two elements in the input array, and so on and so forth. So the last elements in the output array is the sum of all the elements in the input array. And the reduction operation is very useful in log likelihood estimation, because when our data points are independent to each other, the log likelihood, the total log likelihood is actually the sum of each individual's likelihood contribution. And the scan is useful to accumulate individuals in risk set, as we mentioned before. And I will illustrate it in details later. But here, this two graphs just shows the very naive parallelization of reduction operation and scan operation. But the problem is this naive parallelization is not that memory efficient. So that's why we invoke this single pass adaptive look-back prefix sum developed by NVIDIA research group. I won't go into details about this algorithm, but the advantage of this algorithm is it achieves the optimal 2n data movement. It only requires n reads from the global memory and n writes to the global memory. Recall that the access to global memory is the slowest, and we want to minimize it. So this algorithm is by far the most efficient implementation of parallel prefix sum. And if you're interested in it, you can check out this original paper for more details. So let's take a back look of the Cox model. As we mentioned before, the computation of gradient and Hessian is the most computational expensive part in our model fitting, and that's why this is our target for parallelization. And actually, the reason that this part is the most time-consuming part is it contains many double summation here. So each double summation actually requires other n square operations, because like the inner summation requires n operations, and the outer summation again requires other n square operations. But fortunately, we figured out that the inner summation can actually be calculated through prefix sum through scans, that building blocks I introduced before. So here, if we arrange all of the observation by yi in a descending order, which means like y1 is the longest time and yn is the shortest time, then the risk set formulation actually follows a cumulative pattern. And in this way, the inner summation vector is actually the prefix sums of an input vector of exponential x1 beta all the way to exponential xn beta. And actually, all of the inner summation can be calculated through prefix sums. We have so each of the numerator and denominator here can be calculated through prefix sums. And the outer summation can be calculated through reduction. So overall, this is our kernel to perform the computation of gradient and hashes. As I mentioned before, the memory transaction on GPU between global memory and on-chip memory is very expensive. So we want to minimize it. And that's why we fused multiple operations into a single kernel to saving memory transactions. So in this way, we only need to like read the input once and then write the output. So basically the intermediate results will not be written to global memory again. So in this way, we save memory transaction to achieve a better performance of our GPU parallelization. And for fine-grained model, it's very similar. The only difference is the inner summation cannot be calculated through like a single pass scan, but it can be calculated through a forward-backward scan. Since the risk set contains two disjoint sets, we can actually calculate this inner summation as two vectors. So one is a forward scan and the other one is a backward scan. And again, the outer summation can be calculated through reduction. So this figure shows how we do this forward and backward scan. Again, we arrange the individuals by yi in descending order. And the upper part just show the forward scan. It's the same as in Cox model. And the backward scan is the very similar operation in a reverse direction. And with a good parallelization for parameter estimation on hand, now we can turn to another layer of parallelization. Since we usually handle high dimensional data in observational data sets, as we mentioned, we may have like tens of thousands patient characteristics that we want to adjust for. So we need some sort of regularization. And we usually use cross-validation to search for search for optimal tuning parameters. So here, when we use tenfold cross-validation here, but I just show twofold for the sake of simplicity. So instead of fitting each of the replicate in the cross-validation in serial on the default stream, I further parallel each replicate on different CUDA streams in parallel. So basically, we achieve two levels of parallelization. One is within a model fitting, and the other one is across different models in cross-validation. And here I want to pause a little bit to give some tips for GPU programming. So the first thing is when we want to use GPU to speed up our existing program, the first thing we need to do is identify if there is some operations that are suitable for parallel computing. So some building blocks. For example, there's actually many operations that already have very efficient parallel implementation by, for example, the NVIDIA research group. In our case, we use scan and reduction. We use scan because the risk set formulation can be efficiently calculated through scan. And reduction is more useful in many models, not only in Cox model or fine-grained model, because as long as we need to estimate likelihood, and as long as the data points are independent to each other, the total likelihood is the total log likelihood is always the sum of each individual's log likelihood, and it can be calculated through reduction. And we always need to keep in mind that we want to fuse kernels as much as possible. The first reason is we want to avoid unnecessary global memory access because it's very slow. And the other reason is we want to minimize kernel overhead because each time when we want to invoke a kernel, like we need to specify the number of blocks, the threads per blocks, and there's some overhead to invoke a kernel. So we also want to minimize data transferring between CPU and GPU because this memory transaction can also be slow. And now let's look at some results. So here I conducted a series of synthetic experiments across different sample size. And so basically, here I showed both Cox model and fine-grained model. And I showed the time to compute gradient and hashing in dashed line, and this part is actually our target for parallelization. And I also show the total time in solid line. And overall, the GPU is like 40 times fold faster with up to 1 million observations in our simulated data. And these two figures show the multi-thread or multi-stream experiments. And again, GPU is orders of magnitude faster with up to 1 million samples. And here I also demonstrate our parallelization on real-world data. So here I want to estimate the hazard ratio between two first-line anti-hypertension drugs on major cardiovascular disease using new user cohort design. So we're interested in that ACE inhibitor and thiazide in prevent hospitalization for heart failure in the case that a myocardial infarction is the competing risk. And we use the data from Optimum EHR, which is an electronic health records dataset. And in total, we include more than 1 million patients and consider almost 10,000 patient characteristics. And this is the baseline patient characteristics in two cohorts. And we can notice some difference between these two cohorts. And that's why we want to adjust for those baseline patient characteristics, adjust for the confounders. And we simply include all of this patient characteristics. It's almost 10 of thousands into our outcome model. And that's why we need regularization and cross-validation. So here we fit the Cox regression and fine-grained regression with L1 regularization on all variables except for treatment variable. Our estimated hazard ratio is 0.83, which indicates that thiazide is more effective in prevent heart failure. And only hundreds of variables are non-zero after regularization. Remember, we include almost 10 of thousands variables. And what we really care about is the speed up. So the GPU implementation reduced the runtime from 6 days to 13 hours for fine-grained regression. So it's really a huge speed up. And to summarize this work, we develop and apply time and memory efficient single-pass parallel scan algorithm for Cox model and a forward-backward scan algorithm for fine-grained model. And we demonstrate that GPU implementation accelerates the computation of fitting this complex model in large database by orders of magnitude as compared to traditional multi-core CPU implementation. And our future work, the first thing we can do is to extend the current implementation to Cox and fine-grained regression with time-dependent covariates. That would be a little bit complicated setting, but very similar. And we can further fuse cross-validation into a single kernel instead of to parallel them in different streams to minimize data transfer and avoid extra copies of data. And so that's basically my presentation today. Thank you.